So we'll start this lecture by looking at a conventional queue, one that uses mutexes, locks, and then keep on making it smarter, smarter, and smarter. So our basic structure will remain the same. It's a circular queue. You have a head pointer and you have a tail pointer. And every NQ operation as well as a DQ operation is incrementing the head or tail in a modular fashion. So in this case, the basic structure remains the same. Of course, the main function will slightly change. So what we will do is that we will remove the restriction that there is a single NQer and single DQer. That is a restriction that we had in the case of weight-free queues. But we will not have that restriction here. So we will have, it's a free-for-all. So anybody can NQ, anybody can DQ. So we will consider a bunch of threads. And if the thread is an even number, then it will be a DQer. If it's an odd number, it will be an NQer. If you have 10 threads, we'll have 5 DQing threads and 5 NQing threads, as you can see over here. In this case, we'll create a p thread, giving the thread ID as an argument, and the function pointer. The function pointer can either be an NQ function or a DQ function, depending upon the thread number. So basically, what we are trying to achieve is that if we have 10 functions, then we will have 5 NQing functions and 5 DQing functions, right? 5 NQers and 5 DQers. And this is a restriction-less queue. And furthermore, it's also a synchronous queue. So the previous weight-free queue was an asynchronous queue. In this case, we want to create a synchronous queue where you actually wait. You wait for, if you want to DQ and the queue is empty, you actually wait for something to be added. Similarly, you want to NQ and the queue is full, you wait for an entry to be removed. So in this case, our aim is to create a synchronous queue, and the basic structure that we have seen earlier, that is the same. A DQ function just repeatedly calls DQ, and it maps in between. Similarly, the NQ function repeatedly calls NQ and it maps in between. So the thing that we should see, so the new innovation over here is that we are using a pthread lock. So a pthread mutex T lock or a mutex type Q lock, this is basically a lock, and what you need to do is you need to declare it globally and you need to initialize it over here. Initializing this is very simple. It is essentially you provide a pointer to the lock and it will get initialized. All right, so that is all that needs to be done. The second argument is for lock attributes, but in this case, there are no attributes. So we furthermore define these two macros which we will use, lock and unlock. So as you can see, the lockx macro is a simple wrapper on pthread mutex lock, which takes a pointer to the lock object and locks it. And when you return from the function, you are deemed to have acquired the lock. Similarly, we'll have pthread mutex unlock. Again, that takes a pointer to the lock object. And in this case, so this is a macro basically, it's not a function definition. So this is a macro definition. And in this case, you are unlocking, which is same as a call to pthread mutex unlock. So whatever object you specify, essentially its address is sent to pthread mutex lock or unlock respectively. So the code is actually quite simple. It is very, very simple. So what you do is that if you consider the NQ function, you run a do while loop. You run a while loop. In the while loop, what you do is that until the status is equal to -1, you keep repeating. -1 status basically means that nothing was done successfully, right? So you are not able to NQ because the queue is full. So the first thing that you do is, because the queue is a shared data structure, we have to define the queue and we have to create the head pointer and the tail pointer. So here also you will see a new thing, that the queue, the head and the tail have been declared as volatile integers. So they are integers, no doubt, but the reason the keyword volatile has been used is basically because you are telling the compiler not to put it in a register. right? So that is what you're telling the compiler. So it is stored in memory such that the moment it is changed by some other thread, the cache coherence protocol will automatically transport or ferry the new value. Is that clear? So the key idea over here is that if you would have kept it in a register, its value would not have been updated, at least not in a responsive manner, and it would not have followed your memory model, right? It would not have been sequentially consistent. So that is why what you do is you declare it as a volatile int. The moment you declare it as a volatile int, what happens is it's kept in memory, and the cache coherence protocol ensures that any change made by any thread, the value is updated. I mean, all the rest of the replica copies are updated. So once this basic declaration has been done, all that you need to do to access a queue is you need to first acquire a lock on it. So the pthread mutex that we have declared, pthread mutex tq lock, you acquire a lock on it. And then you do your regular checks. So you check if the queue is full, the status is -1. Else if the queue is not full, then you enqueue the entry. We have already seen this part of the code in the last class. So all that you do is you insert the new value at the tail pointer and you increment the tail pointer. So we have a macro for doing that, for incrementing the tail pointer in a modular fashion. So this we have already seen. And then you set the status to 0. 0 means all clear or the operation has been done successfully. After that, you unlock. In case the queue was found to be full, so the status will be -1. So you will keep on repeating until success. Finally, you print this is what you enqueued, and you are done. So we'll now look at the dequeue function. The dequeue function also looks quite similar. So here also what you do is in a do while loop, you repeatedly keep trying to dequeue until success. So first you acquire the lock. So this is a standard pattern. So this was there in enqueue as well. So first you try to acquire the lock such that this queue is the sole, this thread is the sole user of the queue. Then you check for, so then you basically, what you do is that you check for emptiness. And so here you check for fullness over here. In this case, you check for emptiness over here. Say the queue is found to be empty, you set the status to -1, right? The queue is empty. And the fact that this is a check for emptiness was discussed in the last lecture. Otherwise, the queue is not empty, so status can be set to 0, which means all clear. You get the value at the head and you increment the head. And finally, you print that this is the value that was successfully dequeued. So the key idea over here is to define a lock and an unlock, do all your accesses inside it. And if it is not successful, come back again. But it would, if I let's say have this lock call not inside but outside, and this unlock call not inside but outside, that would be incorrect. The reason being that you're not giving a chance to some other thread to run. So let's say that in the case of a dequeue, the queue is empty. You're not giving a chance to an enqueuing thread to actually enqueue. And that is going to be unfair. Not just unfair, you will deadlock. So that is why you acquire a lock, do a single operation, then you release the lock, such that others can acquire it and you keep trying until success. So this is the big broad idea of using a standard mutex lock to design a parallel queue. Alright, so the parallel queue is a concurrent data structure. This is one of the simplest possible designs of a parallel queue. And this is clearly not weight-free, quite unlike the previous example, which was weight-free. But again, it is generic. It allows any number of enqueuers and any number of dequeuers. So let us now look at the same example using semaphores. So in this case, we will use a semaphore as we'll use a binary semaphore as a lock. All right. So semaphore, of course, can do much more. So recall that the semaphore has two operations, wait and post. So wait decrements the count, post increments the count. And in the case of wait, if the count is already 0, then you actually wait. You wait for some other thread to come and post. So is that one of the waiting threads is woken up. And in the case of post, if let's say you're converting 0 to 1, then it's a good idea to check the queue of waiting threads and wake one. So that's the broad idea. So what we'll do in this case is that we will define a queue lock, which is not a pthread mutex, but it is a semaphore. So we will initialize the semaphore in the main function. The rest of the main function remains exactly the same. In this case, we'll create a sem init. The sem init has a pointer to your semaphore. The second argument says, is the semaphore shared among different threads of the same thread group or across processes also? In this case, we are sharing the semaphore across different threads in a thread group. That is why the argument is 0. And 1 is the initial value. So in this case, 1 is the initial value, and the way that we'll use the semaphore will guarantee that it is always between 0 and 1. And in this case, 1 means free and 0 basically means occupied. Right? So the semantics is slightly different. But broadly speaking, we are using this as a binary semaphore, which is like a lock. So you create a sem init. At the end, you have to do a sem destroy, as you can see. So what we will do is that we have to make absolutely no changes to our code. Our code remains the same. All that we have to do, the only magical change that we have to do is actually in these 2 lines. All right. If you see the code, so I will look at the code, we'll compare it, but kindly appreciate these 2 lines first, lock x and unlock x. So lock x basically does a semaphore wait, sem wait, and an unlock x does a sem post. That's all. So I've just mapped sem wait to lock and unlock to sem post. If you look at the code of, let's say, the enqueue function, and if we were to look at the same code of the enqueue function for the other file, right? So you can compare them line by line. So you will see that the code is exactly identical. Sorry, let me just align it maybe. So you can see that in a line by line, the code is absolutely identical. There is no change whatsoever. It is the same code that runs. Similarly, if I were to compare the dequeue function, you will also find that the same code is identical, right? There is no change whatsoever. It's the same thing that runs. And the magic here is that the lock and unlock macros, they are not using a pthread mutex t, but they are using a semaphore. And it's a binary semaphore. It is working like a lock. So no change needs to be made to the rest of the code. Everything works magically. That is the magic of semaphores and the magic of writing the code such that changes done at the high level do not require changes to be done at a lower level. So you simply redefine lock and the lock and unlock macros, and that is all that needs to be done. All right. So we are still not using the full power of semaphores, which can be quite disconcerting to many, but we will very soon do that in our next example. So let's first appreciate this example a little bit more. So we are basically saying that locking is same as sem waiting, and that should be obvious if it is binary. That if it is 1 means the lock is not taken, so I convert 1 to 0. Subsequently, whoever comes will wait on 0 until the lock is released. Then any sem post will release the lock, one more thread will come in, that will release the lock, one more thread will come in. If there are no more threads, the last sem post, so in this case, every sem wait is paired with a sem post. So finally, if there are no other lock contenders, the value of the semaphore will become 1. Now what we will do is we'll look at the 4th example. So in this case, we will actually use the power of a semaphore, right? So we will use the power of a semaphore to kind of get more parallelism, right? Instead of a single lock, which is slightly, so also in the single lock, you'll have to do changes to see if the queue is empty and full. So all of those emptiness checks, fullness checks can be done via semaphores in a very natural way. So let us look at how and why that is to be done. So the same thing, in this case, we'll define a wait and post macro, not lock and unlock, because we are not using a binary semaphore anymore. So wait is basically a wrapper on semWait, a post is a wrapper on semPost. All right. And then we have, 4 threads here, 40 iterations, that doesn't matter. So we are creating 3 semaphores here, not 1, but actually 3. One of the semaphores, semQlock. So we are using a QLock. A QLock in this case is a binary semaphore. All right. So a binary semaphore is acting like a lock. Then we have 2 more semaphores that we will use to infer emptiness or fullness. The first semaphore is called empty, and its starting value is buff size. Buff size is buffer size, the maximum size of the queue. All right, so we will see. This is basically the number of empty slots when you begin. So when you begin, the entire queue is empty. And how many entries does the entire queue have? It has buff size entries. That is why when you begin, the entire queue is free. And when you begin, the entire queue is not full. So ideally, you want, if steady state sets in, that the empty entries plus full entries is equal to the total number of entries. So initially, nothing is full. So that is why the count is 0. So the sum total is, we have 3 semaphores instead of 1. 1 is binary and 2 are non-binary. The rest of the code remains the same. Let us look at the NQ and DQ functions. So in the NQ and DQ functions, what you do is that you sort of detach the work of updating the queue and checking for emptiness or fullness. So even before looking at the code, let's just understand. The NQ function does 2 things. The first is it checks for fullness. If the queue is full, it will not do anything. It is going to wait. Once there is a free entry, then it will try to update the state of the queue. So updating the state of the queue, let's keep that separate. Let us say that updating the state of the queue is encapsulated in these 4 lines, where you acquire a lock on the queue, which is you wait on QLock, and then you NQ. And we have already seen this piece of code in lines 32 and 33. So I'm not going over it once again. And then you release. So this part is basically updating the state of the queue. What we need to do now is we need to do a few more things. The first is we need to check if the queue is full or not. This is the same as checking whether there is any empty entry or not. Right? So if there are no empty entries, then you should wait. That is why you wait on the empty semaphore. Initially, let's say the buffer size is 10. Then this is 10, you wait on it, it will become 9. Then 8, then 7, then 6. If it ever becomes 0, then you wait for it to become non-zero. Similarly, when something is added, you are creating a full entry. So you should post it to full. This is like removing one entry from empty and adding it to full. Every wait empty is paired with a post full, which is like the moment I'm adding something, it is one less empty entry and one more full entry. So something is being transferred from here to there. All right. And in case empty is 0, it means there is nothing. There is no free entry, so I wait. All right. In a similar manner, let us look at DQ. In the case of DQ, again, I detach the functionalities of checking for emptiness, fullness, and updating the queue. So let us again look at the 4 internal lines. So in this case, I wait on the queue lock, right? I wait for it to become available. Once it is available, I update the queue. And updating is very simple. I read the value at the head and I increment the head. So this part we have already seen. The important part is, when I'm dequeuing, what do I want? I need at least one full entry. That is why I wait on full. If it is 0, I wait. Otherwise, I decrement. Once it is done, what do? I have dequeued, which means I've created one extra empty entry. So I post to empty. So this is doing the reverse of this, is removing something from full, one entry, and putting it in empty, right? So the direction of the transfer is reverse. But broadly speaking, you can see that we can sort of naturally, using semaphores, using this elegant mechanism, create a method to signal between the NQ and DQ functions and figure out emptiness and fullness quite easily. And once this is done, nothing more needs to be done. And also the size of the critical section, which is this part, has reduced substantially. Because previously the check was within the critical section. Now it has been removed outside the critical section. So that part has become somewhat fast. So this is clearly a more scalable and natural design. And it is using semaphores, which is actually the strength of a semaphore. So now let us slightly complicate the example. Let us assume that along with the NQ function and DQ function, we have an additional peak function. The peak function looks at the head of the queue and simply returns its value. So the NQ and the DQ change the state of the queue, so they are write operations. But the peak function that only looks at the contents of the head is fundamentally a read operation. So we would like to use a reader-writer lock, which, if you would recall, we had designed it fully. Which, if you would recall, it basically said that we can either have all readers, right, only readers and more than one only readers, or a single writer. All right, either just one single writer or just a set of readers. Which means that in this case, a set of readers can concurrently peak the queue, or a single writer can do an NQ or DQ. So we want to have that kind of a system. So what we will do over here is we'll define 4 semaphores. So we will have, so if you would recall, in the reader-writer lock, we actually needed 2 locks. We needed a read-write lock and a read lock, right? If you would recall the code, we needed 2 locks. So we are creating 2 binary semaphores. And then our regular empty and full are there. The main driver code slightly changes in the sense we create 3 different kinds of function pointers: NQ function, DQ function, and peak function. The rest is all the same. So all that they do is they take a nap and keep NQing, DQing, and peaking. So all of this is simple stuff. So let us first look at the peak function. So we will look at the function, we'll look at its implementation later. So this is something that you have also seen, right? You have seen earlier when we were discussing a reader-writer lock, you have already seen. In this case, let us say I want to peak. So peak is a read operation. So I need a read lock, which will allow me the permission to read but not to write. So all that I will do is I will call get read lock. How it is implemented is none of my concern. So right, so one of the key ideas in designing any computer algorithm or code is that you write it sort of from your point of view. That I will use these functions. This is what they are going to do. They are going to do means this is what I'll give them, this is what I expect in return. All right. How they achieve it is none of my concern. Okay. So that is typically how you break a large problem into a small set of small problems, where you say that, it will have these small functions. They will do their job. How they are doing, I couldn't care any less. In this case, I am saying get read lock. Get read lock means somehow acquire a read lock and give it to. After that, I check for emptiness. And if it is empty, then, so in this case, the peak function, I make it wait free. If it is empty, I return -1. Otherwise, I return the contents of the head. Right? So far, so good. And anyway, I have a read lock, so I can read. There is no threat of a writer. And then I release the read lock. All right. And whatever value I write, if it is -1, let's say that the convention is it is empty. Else, you return the value. So it is as simple as this, where this is a declarative style of programming, where you are saying that this is what I need. How it is implemented, we'll see later, or someone else will see. Let us now look at the NQ function. So NQ function is the same, barring a little bit of a difference. So wait empty and post full are still there. So we recognize this from the previous algorithm. What has changed is basically this part, where again line numbers 57 and 58 are the same. This we recognize as a standard algorithm to insert something into a circular queue, which we have seen. The only change is line number 55 and line number 60. In this case, we acquire a write lock and we release a write lock. That is all. That is the only change. This is because an enqueue option is a write. So all that I am concerned is somehow give me a permission to write. The fact that I am returning from the function is the permission to write. And then I go ahead, do a write and I release it. Similarly, in the dequeue function, wait full and post empty are there. I acquire a write lock. I update the state and I release the write lock. All right. So how I do is a separate issue, but I need permission to write. That is what I get. Get the write lock, I do the write and I release the write lock. All right. So this part is your basic reader-writer code. Of course, we have not defined these functions. We'll define them shortly. So now we will look at how these get write lock, get read lock, etc. are implemented. So this is the same code that we have been seeing. So we have seen in the last class and the class before that. So we have a global read write lock, and for a get write lock, you simply acquire that, which is same as waiting on the semaphore. And in this case, releasing it is same as releasing it. The main sort of intelligence goes in creating the read lock, where what you do is that you get the wait on the read lock semaphore first. If the number of readers is 0, there is a possibility that there could be a writer. If there is no writer, then you would like to block off the writer for perpetuity. Well, not for perpetuity, till there are readers, right? Obviously, that would be unfair. So you wait on the read-write lock, which means you acquire it. After that, you increment the number of readers and you release the read lock. Similarly, when you are releasing the read lock, so the read lock semaphore is protecting readers. So it has to be acquired first. So you acquire the read lock semaphore and you decrement the readers. If the number of readers becomes 0, then there is a need to release the read-write lock such that if the writer is waiting, the writer can get in. All right. Otherwise, we'll be blocking it for perpetuity, which is a bad idea. That is unfair. So then, if there are no readers, then if there are any writers, let them come in. And then you release the read lock, which is a lock on this variable. So this is our own reader-writer lock library, which works in this context. So you can download it from the website, you can run it, it should run just fine. And it does enqueuing, dequeuing and peaking in a reader-writer context. So we'll next discuss condition variables. So you think of semaphores as sort of a generic OS mechanism, then condition variables are also generic. So semaphore basically allows a complex pattern where one thread waits on some variable. If that variable is 0, then something happens, else something else happens. So a condition variable is something which is quite similar. So in this case, what happens is that so you create a condition variable and always a lock is associated with a condition variable. So we'll see in a second what it is. So it allows a generic method for one thread to send a signal to some other thread to wake it up. In the case of a semaphore, you have a reasonably well-defined interface, right? You have a sem wait and sem post. So if you are waiting, someone else is posting, then only the waiting thread can wake up. So this situation is slightly more generic, where you have a condition variable and you have a mutex associated with it. So in this case, what happens is that if you want to wait on the condition variable, so in this case, it's like a generic waiting, that I will just wait, I want somebody to signal me. So what you do is that you first acquire the mutex. That is mainly to protect the state that is there within the condition variable. So you acquire the mutex, you lock it, and then you do a cond wait, which means on this condition variable, you wait using this mutex as the mutex that will protect its internal data structures. The moment you wait, what happens is that the library releases the lock. It releases mlock. Then some other thread that can signal you. So some other thread needs to do exactly the same, acquire the mutex, and then basically send you a signal. All right. So when you send a signal to a condition variable, what happens is that you wake up one of the threads that is waiting on it. So when you do a cont signal, it will wake up any one of the threads that is waiting on it arbitrarily. When the thread wakes up, it will reacquire the lock, and then it can do some things and ultimately release the lock. All right. So this is a generic way of me just going to sleep and somebody else waking me. And instead of cont signal, you can use cont broadcast. So cont broadcast would kind of wake up all the waiting threads. So far, so good. All right. So cont broadcast, whoever is waiting will be woken up, right? Waiting on that condition variable. There are a few more things. So barriers are heavily used in high performance computing. So let us say that you want to add 1,000,000 numbers. And there are 10 threads. So how will you do it? You will divide the 1,000,000 numbers across the 10 threads. Each thread will then add the chunk that has been assigned to it. So let's say that this is S0, this is S1, this is S2, so on and so forth. If there are 10 threads, there are 10 chunks, and each chunk has a sum, partial sum. So you need to wait for all the threads to finish. Only when all of them have computed their partial sum, like a map reduce, then what you do is that you will get all of those partial sums and add them. And that will be your final sum. So waiting for all the threads to finish means what? You define a common point called a barrier and let all the threads reach it. If any one of them reached it first, let it stop there. Then let's say the next one, so let all of them reach it, and then you can release all of them at the same time. All right. So this is like a point where you say that even if a thread is slow, the fastest thread will wait for the slowest thread. So let all the threads come here. And then after that, what I will do is I will release them in one book. So this kind of a synchronization things at this point, let's say that one of the threads can then after this point be given the responsibility of collecting the partial sums, and adding them and displaying the result. And the other threads could move on to doing other things. All right. So you have a slightly more sophisticated form of a barrier, which is known as a phasor. So phasor says that before you cross point 2, all the threads have to reach point 1. Is that clear? So before any thread is allowed to cross point 2, all of the threads have to reach point 1. So this you can use for other kinds of applications, right? Where you are actually defining not one but 2 points of interest. The first point is where you want everybody to reach. But then in the barrier, point 1 and point 2 are the same. But in this case, point 2 is slightly advanced, like later in the future. So basically, even if you have reached point 1, you can go a little bit ahead, but you cannot go very much ahead. All right? Because if you go very much ahead, then the distance, the divergence will increase. So that is why what you do is that you stop at point 2 until everybody has reached point 1. Does that make sense? So if I look at the previous example of taking an array, let's say with 1,000,000 entries and breaking it down. So point 1 could be the point at which all the partial sums have been computed, right? And point 2 could be a point where this array is actually replaced by another array. All right. So you should not replace this with another array until the previous array is being used. That is why what you can do is you can wait for everybody to reach point 1, which means they've used the previous array and they have secured their results. After that, some thread can exit point 2 and do something else which may involve replacing this array as well. So we have now come to the end of this lecture. So then the next lecture, we will actually start looking at what happens inside the kernel and look at some scheduling related problems. So as I have said earlier, that for understanding the space of scheduling, especially multi-core scheduling, it is important to have a very thorough and sound idea of NP completeness. So before that lecture, so this is a prerequisite for the entire scheduling lecture, which is all of this. So this does not require NP completeness. This is simple algebra. This is simple math. So real-time scheduling is actually a lot of fun, but it is simple arithmetic. This part requires some knowledge of NP completeness, and so we will start that shortly. But this is kind of an advice to have this prerequisite before we go there.